Hi, in this segment we're going to talk about a typical mud motor and all the parts that go into making it up. I'm going to be spending a few minutes showing you how each part functions and just generally how they look, so that if you ever needed to know this, you would have it for your reference. I've separated the tool out here into rotating and stationary components. The stationary are the darker colored components in behind, and although they're not threaded together, you can see that they're lined up as generally as you'd find them in the built tool. The rotating components are all the lighter colored ones, which are shown in front. Okay, I'm going to start at the front end of the tool and move downwards with the rotating components first. So if we start at the top, your tool may have a rotor catcher installed. I'm going to explain the function of each piece afterwards. For right now, I'm just going to point them out so that you know what they look like. So this would be a rotor catcher. This is a catcher ring. This long shiny piece in front of me is a rotor. You can see that it's shiny. It's got chrome on the outside of it. If we move down to the bottom of the rotor here, this is the rotor box at the bottom. You can see some rotors will have some ports on it like this. This is the CV assembly directly below it. It's basically symmetrical. It's got a pin connection at the top. It's got a cap, a shaft which transmits the torque generated by the rotor. And it's also got a bottom pin connection here which gets threaded into the drive shaft cap. The drive shaft cap has got some fluid ports on it. And if we look at the bottom of the drive shaft cap, it's also got a box on it. Below the drive shaft cap, we thread the drive shaft directly into it. And this piece actually isn't there. It's just a protector to make sure that threads don't get damaged during this filming. If we move on down towards the bottom of the drive shaft, this would be the part that you'd normally see on the rig with the bit box on the bottom, and the bit would just get threaded strictly directly into the bottom of the drive shaft. If we move to the stationary components, the first one I have right in front of me here, this is the lower bearing sub. And this is the only connection in the entire mud motor that's got a left-hand connection. And if we go above it, we have a bearing housing, and it's, as its name suggests, simply a housing to contain all the thrust bearings in the tool. You can see on the outside of it, it's got this location here, some threads for a sleeve stabilizer. It's also got an upset to protect the threads and make sure that they don't get damaged. Continue to move upwards, we've got a box at the top end of the bearing housing, and we've got an adjustable bend housing assembly that we're going to show here. There could also have a fixed bend housing assembly. The first component that I'm looking at is the offset housing. You can tell it's the offset housing because it's got the little milled windows in it with the numbers on it, and it's the longer piece. The adjusting ring goes above it. It's got a pad on the back side which is protected by some carbide buttons so that it doesn't wear too quickly. It's also got some milled numbers into it. If we move above the adjusting ring, we've got the stator housing adapter, and this is basically just a connection to go from the top end of the adjustable bend housing to the stator. This would be the lower stator box, and the stator just looks like a basic tube. We're going to see a little bit more about the stator when I show it later. If we move to the top end here, this is the upper stator box, and into that we would screw the upper saver sub, which I've got in my hand right here. Starting at the top end of the tool, we see a couple of things. First one here is the external housing I'm going to point out. This is the upper saver sub. It's got a right-hand pin connection on the bottom of it, and it's got a rig connection on the top. This is a 6 3/4 one, so it's probably got a 4.5 IF connection on top. The upper saver sub is strictly there just to protect the stator threads. These are the modified Acme proprietary Sperry Sun threads, which are used and are quite thin. So in order to cross them over to the rig connections, which tend to take a lot of damage, we've put on this saver sub here to basically protect these threads and make them last longer. If we move over here, this is the rotor catcher that I pointed out earlier. The rotor catcher is essentially screwed onto the top end of the rotor in the event that the motor should come apart for whatever reason. The theory is that the rotor catcher should be able to catch the lower components and prevent everything from actually falling apart. You could pull out of the hole and not lose anything down hole. The idea is that this ring here, called a catcher ring, is installed into the ID of the stator, with this diameter being slightly smaller than the ID of the stator. It would then sit right on top of the rubber, and in the event that any of the connections should part, this catcher sub would essentially come down and jam on this lip. When it jams like that, it should be capable of supporting all of the components below it, and that's what would allow you to pull out of the hole and not leave anything behind. If you didn't have a catcher assembly installed, then you'd simply have a rotor jet sub assembly, like this one shown here at the end of the rotor. And this one is shown blanked off, but in some cases you may want to jet the rotor, and it could have a hole in it. This is the rotor and stator in front of me. The rotor is obviously the rotating piece of equipment, and the stator is the stationary piece of equipment. If we look at the rotor first, you can see that it's really shiny. It's got something called chrome, which has been applied to the outside of it. The entire idea of the chrome is that it provides a hard, wear-resistant surface and makes the component last longer. Typically, rotors are made out of stainless steel, so we don't have any corrosion problems. The stator, on the other hand, is just basically a steel tube which has got rubber that's bonded to the inside of it. And although I can't show you this particular stator in front of me, I got some smaller rotor and stator samples that I can show you to try and point out how they work. So if I look at this one first, you can see that you've got the shiny metal surface on the outside here. You've got rubber which has been bonded to the inside. You can see that this one's got this funny profile that's built on the inside, and actually it's been molded right into the rubber. If I look at the mating rotor component, you can see that it's got a similar profile cut on the outside of it. What we find is that in order to make this tool work properly, we have what's called the reverse Monod principle, or the positive displacement motor, PDM. The way it works is we normally have one extra slot or groove in the stator as compared to the rotor. So if I look at this particular one, I'll put one down just to help count. If I look, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lobes on the stator. And if I count the rotor, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 lobes on the rotor. So this would be what we would call a 9-10 lobe configuration. Now if we compare that to this other sample that I've got, this would be what's called a 1-2. So if I look at this one, this knob, by the way, is just to hold on to. It's not actually part of the rotor. This one looks like a corkscrew. And you can see that if you look on the end, it's only got one lobe. And if I look into the mating stator, you can see that it's actually got two cutouts here. So it's got two lobes in it, so we would call that a 1-2. When we look at a rotor and stator when they operate, we find that there's a general trend to the number of lobes and what the motor will actually perform at. And the correspondence is that the more lobes, the higher torque and the lower speed. So for example, if we looked at the two extremes that I've just shown you, the 9-10 rotor and stator would be a high torque, low speed tool, and the 1-2 rotor stator combination would give us a high speed, low torque combination. This is the adjustable bent housing assembly. It's actually made up of 4 parts. As I pointed out earlier, we have a stator housing adapter, an adjusting ring, we have an offset housing, and this is the internal piece called the spline mandrel. You can see the spline mandrel has got some splines cut into the outside of it. That's what prevents it from rotating when it's all threaded together. It's got pins on both ends, and if you look carefully at this one, hopefully you can notice that this top pin is actually offset. So it's not cut on a true vertical, it's actually slightly offset. If I try and rotate it a bit for you, maybe it'll be a little bit more obvious. So this pin is actually machined offset. That'll be important in just a second. If I roll it out of the way, you can see that the numbers for the offset housing and the adjusting ring are actually milled right into the outside, and I'll show you how to line those up in a second. If you look on the top of the offset housing, you can see it's got some teeth on it. These teeth are going to match up with mating teeth on the ID of the adjusting ring. So if I slide them together, you can see that they will engage, like so. And on the back side of the adjusting ring, there should be a pad which will line up opposite the high side of the tool, and we've got it all put together. That pad will prevent wear and hopefully make these components last longer. Finally, we've got an a stator housing adapter which mates up to the adjusting ring. The way the adjustable bend housing works is the face of the adjusting ring is actually machined off-center, similar to the machining that was done on the spline mandrel. That eccentricity, or that misalignment when you rotate these two pieces, is what will create the bend in the tool. So rather than trying to work with all these really large components, what I've done is I've actually got a smaller assembly right beside me here that I can operate by hand, and using that I'm going to demonstrate how this tool would actually be bent and how we'd actually do it once we're on the rig floor. So if I just point out the pieces really quick, you can see I've got an offset housing on the bottom. I'm going to rotate it so you can see all the numbers here. Here's the offset housing. Got an adjusting ring. Here's the pad on the back side that I was telling you about earlier. And then we've got a stator housing adapter on top. And of course the spline mandrel's in the middle holding this whole assembly together. So if I can get you to zoom in here, what I want to point out is that right now this assembly is set on 0 degrees. And the way I see that is because I've got the two 0 lines matched up here in the middle, indicating that it is indeed set on 0. If you pan back and look at it really closely, you can actually visually see as I rotate the part that it's not bent. It's essentially straight. We can pick that out by eye. Okay, now if I want to adjust this on the rig floor, the first step would be to back off this top connection here between the adjusting ring and the stator housing adapter. If you're grabbing this with rig tongs, you'd like to try and avoid grabbing onto the adjusting ring. It does have these carbide buttons that tend to be brittle, so if you can avoid those, that would sure be good. And what I'm going to do is I'm going to back off this stator housing adapter 2 turns. It should not be necessary to back it off any more than 2 turns. So if I use this milled slot as a reference here, I'll just rotate it around 2 times. That's once. And that's twice. At this point, it should be possible for me to lift up the adjusting ring, just like I've done, and I'm now free to rotate it because I've disengaged those milled teeth that I was pointing out earlier. So if I want to set this on the maximum bend setting, which in this particular case is 3 degrees, I'm going to rotate the 2 angles relative to one another, trying to match up the 3-degree markers on the assembly. Now if I can get you to zoom in here before I drop down the adjusting ring, you can see I've got 3 degrees indicated on the adjusting ring and 3 degrees indicated on the offset housing. When I've got it's lined up like that, I set down the adjusting ring, the teeth engage and the lines will line up. At that point I make up those 2 turns on the stator housing adapter, just like I took apart earlier. And we've now got a 3-degree bend setting in our adjustable bend housing assembly. If I rotate it, it should be obvious. You can see that this assembly is definitely bent. And we've achieved our goal. This is the CV assembly. Now we've got 2 problems working against us. First of all, we've got the adjustable bend housing assembly that I just showed you, which is going to put a bend into our tool that we're going to use to be steerable. The other problem is that the motion from the rotor, the rotation, is actually eccentric, which means that it doesn't turn in a true circle. It actually wobbles in some sort of an eccentric path. So we need to have some sort of a device that's going to be able to handle these 2 problems. We can do that with the CV assembly. It stands for constant velocity or universal joint assembly. If we look at the components that make it up, we've got a shaft in the middle here. It's got some milled ball pockets on the end of it. We've got a boot because it's going to ride in an oil cavity. We've got a cap that sits onto the end of the coupling. And if we look onto the end of the coupling, we actually can see that there are some milled grooves into the end of it here. It's also got a round radius for the thrust component that'll sit right in the middle. So if I put this whole assembly together, normally I'd slide the boot on first, but to try and keep things clear, I'm going to not do that in this case. I'm going to put the cap on. The next step is to install the torque balls in here, which is actually going to prevent the coupling from rotating. And if I can show you a little trick here, hopefully I can hold all these in place and slide it on at the same time. And I'm successful. And now I'd bring the cap on over top. Bear with me as I slide the cap on. And the cap will eventually shoulder up on the end of the coupling. Like so. Okay, now what I want to demonstrate is I can't rotate because the torque balls will prevent me from doing that. So that's what transfer the torque from the rotor on through to the bottom part of the tool. Well, at the same time, I can still move back and forth like this, allowing for the flexibility of both the bend and the eccentric motion of the rotor. Finally, I've got a built assembly which I'm going to show in front of you. This is what it would actually look like when it's actually put together. And you can see that the boot's been put in place. It's got oil in the cavity underneath here. There's some banding on either side. You can see that the cap has been torqued up to the coupling end. And if I move in and rotate it, it's a little stiffer than the other one I showed you, but essentially it moves just like the other one does. This is the last sub-assembly that we're going to talk about. This is the bearing pack, or the bearing assembly. And before I describe to you this particular one, I wanted to let you know that there's actually several different designs of bearing pack that may be available to you. The one that I'm going to show you here as just a typical version is the original Sperry drill mud lubricated can type bearing assembly. So if we start from the top, we'll find out that there's usually a lock nut, or we call it a drive shaft cap, that sits at the top of the tool. You can see that it's got ports here at the top. What we're going to find is that the mud lubricated bearing pack actually uses the mud or fluid to cool and provide lubrication through all the rotating elements, rolling elements that are inside it. But only a small proportion of that fluid gets used for this cooling and lubrication, generally between 5 and 8%, depending on a few factors. So that means that 92% to 95% of the fluid actually has to go through these ports here, and you can see that there are 4 of them on the outside of the drive shaft cap. Have to go through these ports and down through the hole in the middle, which will eventually go through the drive shaft and come out through the bit. So the vast majority of the fluid traveling through the mud motor gets pumped out the bit, but a small proportion of it actually gets used for cooling. On the outside of the drive shaft here, we've got a chrome section. And this chrome section is used to provide what's called radial bearing support. Radial bearing support means that the eccentric motion that was coming off the rotor and through the CV assembly will get brought into what's called concentric motion. So rather than rotating around in some sort of wobble, we'll take it so that it's got a nice smooth rotation about a concentric axis. We do that by putting this in a radial bearing. We've actually called it a marine bearing. And if I stand this drive shaft cap up, I can point out the marine bearing beside it. You can see it's got a brass shell on the outside, and on the inside it's got some rubber bonded to the inside of the brass shell. Well, the chrome, again, is a wear-resistant surface, which is designed to be long-lasting, and when we put the marine bearing over top, you can see that there's a fairly snug fit between these two components, and that's essentially what's going to hold it concentric. Okay, below the radial bearing assembly, if I set this back over, remember the drive shaft pin gets threaded into the bottom of the drive shaft cap. The next component that I'd like to show is the flow restrictor. Now remember, I told you that most of the fluid goes through the drive shaft, but in order to prevent the bulk of the fluid from coming through the bearing pack, we've designed an assembly called a flow restrictor. This is really the guts of it right here. If I pull this internal piece out, you can see that this piece, I don't know how well it's going to show up on camera, but hopefully you can see that there's actually a steel piece bonded to the outside of a tungsten carbide, cemented tungsten carbide internal ring. You can see it's got this smooth radius on here. What we do is we drop another piece of carbide inside it, and it's a fairly tight fit. You can see that there's not a whole lot of clearance in here, and that all the fluid essentially gets forced between these two pores, the space between the two components. You can see that with all of the volume that I showed you in those ports in the drive shaft cap, the bulk of the fluid would go down through the cap, and very little of the fluid would actually get past this flow restrictor through the bearing pack. So we actually don't see that in the final assembly. This is all housed inside of an outside cartridge. We'll see that in a few minutes. Below the flow restrictor assembly, we've actually got a thrust bearing assembly. Thrust bearings are designed to handle the axial loads that are occurring along the length of the drive shaft. So we either got an on-bottom compressional loading, or we have an off-bottom tensional loading pushing and pulling on the drive shaft. Thrust bearings are used to allow us to rotate the components and be able to put these axial loads on them at the same time. So remember, I told you earlier that there may be a couple of different thrust bearing assemblies in use. This is the original can type cartridge assembly. You can see it's made up of two races, the stationary one down here at the bottom. It's got a bunch of balls, and we've got a rotating race up here at the top. And if I put one on top of the other and rotate it, you can see that it spins quite freely. If I use it now to build up a typical bearing cartridge, if I move over here a little bit, you can see I'd put the stationary can over top of the rotating sleeve on the inside, and if I can drop this part in there without spilling all the balls. Stationary bearing sits down at the bottom. Drop all the ball bearings. And then finally the rotating bearing race will sit right on top. So that's the cartridge assembly, and there will be a series of these directed in two directions. I'll show you what I mean by that when we look at the final assembly in just a second. Finally, as we move over to the bottom part of the assembly, you can see that we've got another marine bearing and another chrome surface which has been applied directly to the drive shaft. This is another radial bearing exactly like the one that I pointed out earlier, and you can see that this is essentially the same marine bearing, just a different length. If you look inside it, you can see that it's got rubber bonded to the inside of a brass shell. And if we look at the final bearing behind me here, you can see that this is what it looks like when it's actually pressed into the lower bearing sub. Finally, I've got the bearing housing, which I'm showing right above here, and the upper marine bearing has actually been pressed inside of the top part of the housing. It's going to be pretty tough for me to show you that. And essentially this thing is just going to slide over top of the entire bearing pack assembly as we have it stacked up. This is the final assembly before the bearing housing has been slipped over top. You can see that I've got the drive shaft cap on top. This is the flow restrictor cartridge. You can see that it's housed in a container. We've got a spring on top of it, which is going to provide all the compression to make sure that none of these outside stationary components are going to rotate. can see the cartridges that I was talking about. You can only see the outside cam, but all those internal bearings are all inside each cartridge. You can see that there's 1, 2, 3 of them in this case. We've got something here called an inverter ring, and this is each one of these cartridges are actually unidirectional, either on bottom or off bottom loading. So we've stacked them up in a certain order, and at one point the whole cartridge is flipped around, and we need an inverter ring to allow us to do that. You can see that we've got several more bearings below it. So this particular assembly has got 6 cartridges in it. Got something called a lower spacer ring, which sits right on top of the lower bearing sub that has the marine bearing inside it. So at this point, the only thing left to do is to put some O-rings on the flow restrictor assembly here and slide the bearing housing over top and make it up. Well, that will conclude the parts of the mud motor. I think you should bear in mind that although this particular mud motor is a typical mud motor, 6 3/4 in size, remember that there may be other sizes, either bigger or smaller, running right through from 3 3/8 up to 11 1/4. And also bear in mind that although they're different in size, the principle behind the components that I've shown you here are essentially the same.